Good evening, everyone. I think my voice is visible to everyone. Okay, we are here for class 7. Before starting the class, we'll go through what we had seen in the previous class. Okay, and then we'll start with today's class. So it's actually we are going to do continuation of the mechanism section. So we'll just brush through what exactly we saw in the class 6. Okay. Before that, just let me open the assignments as well, and then I will start taking this. Yeah, so in class 6, we were looking into the single electron transfer reaction, which says there is no, what to say, any adsorbed intermediates involved. Whatever is formed, it gets directly transformed into the product. Okay, so that was what was the single electron transfer reaction. Then we moved on with two-step reaction where we have single adsorbed intermediate involved. Unlike the previous case, there is one adsorbed intermediate which is getting involved in this. So let's see, the first mechanism that we saw was the reaction mechanism analysis of a Caroferry couple where the Fe2 plus is getting converted to Fe3 plus and there is no adsorbed intermediate. It's a single step reaction which is happening. If I write, it's like A um giving B plus 1 electron as a forward reaction and a backward reaction. So the rate of the reaction is nothing but it is the rate constant into the reactant minus rate constant of the backward reaction minus the concentration of the product. And here we know that the rate constant is actually exponentially related to the potential, DC potential we are applying. So if I give the same substitution, it becomes something like Kf naught e to the power Bf EDC into Fe2 plus minus Kr0 e to the power Br EDC Fe3 plus, where B is the factors which are related to charge transfer coefficient as alpha NF by RT for the forward reaction and minus 1 minus alpha NF by RT for the backward reaction. So the first step when you're given such a mechanism is to write the rate of the reaction, and the next thing we have to calculate the charge the current density. Okay, and that is related to NF into the rate of the reaction. When we substitute, we'll get this. The rate of the reaction we'll get from the previous step, that is uh, NF Kf naught e to the power Bf EDC into Fe2 plus minus Kr e to the power Br EDC into Fe3 plus. Then we are looking into the linearization part. Linearization, why we are doing in order to express the rate constant in terms of uh, the DC rate constant, and because it is EAC, that is the AC potential is also applied, we have to also account for that. So EDC plus EAC is the sum total of the applied potential, and EAC is actually sine wave, EAC not sine omega t. And same thing goes to the rate constant expressions. We have Kf, which is related to exponential to Bf into E. When it's AC current is also applied, we have to write as A because both E, because it has both the DC component and the AC component. We are then subtracting out this part and e to the power Bf into EDC plus EAC, which becomes e to the power Bf EDC into e to the power Bf EAC. So this part, that is Kf naught e to the power Bf EDC, we write it as such, and the other part we are expanding. Why? Because value we can actually elaborate it for e to the power x as e to the power x equal to 1 plus x square by 2 factorial, etc. Same thing we are doing here. And Because it is a small value, we are truncating it after the second power. Now, kf naught e to the power bf into edc, this is nothing but the rate constant for the dc part. So, we write kf dc and 1 plus bf into edc. This is what we get the rate constant as. Now, for any small overpotential, the linearization is applicable. So, same thing, we are substituting for the rate of the reaction. Here we wrote initially the rate expression where Kf and Kr is Kf dc into 1 plus Bm Vac and Kr dc is Kr dc into 1 plus Br edc. We substitute it, we rearrange it, we get If, and we know that we'll have both the parts. One due to If, the current density because of the DC potential, and the current due to the AC potential which is applied. We separate it out the If DC, whatever remaining we get, that is If AC. This is how we find out IFAC. Once we get IFAC, we will be taking out EAC from the expression, and then we know impedance is nothing but it is EAC by IFAC, and we rearrange. So this part ZF, that is because of the reaction, because impedance due to the reaction. Now we need to find out the total impedance. We have to also accommodate for the impedance due to the doubling capacitance, and that is 1 by j omega CDL. So both are in parallel due to the Faraday reaction, and because of doubling capacitance, both are in parallel. We write it, we do take the inverse of the reciprocal, and we rearrange it. We get something like this. So this is the like the methodology or how we have to proceed for such a question. We have to first find the rate of the reaction. Then we know the linearized value for the rate constant, and then we find out the charge transfer coefficient. Sorry, we find out IFDC and IFAC, which is not nothing but the current density. Then from that we separate out IFAC, and then we take IFAC by EAC. We will get the impedance. Okay, the admittance or the impedance form, and then we find out the total impedance by considering the double layer capacitance also. So this is how we have to proceed for such a question. Okay, I hope it's clear. Now let us move on to the next one, which is two-step reaction. The two-step reaction where we consider with single adsorb intermediate. We are going to consider where there is only one intermediate. We say that unlike the previous one where the product is formed in a single step, here it doesn't happen so. Here we say that the reactant initially becomes an adsorbed intermediate which then goes into the solution. So the step one involves, if you see here there are two steps. The first step involves an electron transfer and the next one doesn't. The first step, because it involves an electron transfer, we say it's an electrochemical reaction, and here the rate constant becomes a function of the potential. In the next step, there is no electron transfer involved, so it's a chemical step, and here the rate constant is a constant. It's constant or it's fixed, it doesn't change with the applied potential. We say that on the surface of the material, the total number of adsorbed, like the total number of active sites are gamma, and the fraction of the surface which is adsorbed, which is covered by m adsorbed plus of that adsorbed intermediate, we say it is theta 1. So vacant or the available site fraction is 1 minus theta. Now mass balance equation, we will write gamma d theta by dt, which is the consumption mass balance for the intermediates. That's based on the rate of consumption or the formation of the adsorbed intermediate with time. Gamma d theta by dt equal to rate of formation minus rate of consumption. And rate of formation, what is the rate of formation? It is K1, that's a forward step. So in the first step, adsorption is formed, and the next step, adsorption is consumed. So here it becomes K1 into So what is the concentration of M, the metal that's in the unabsorbed surface, which is 1 minus theta. The next step, because it is getting consumed, we write as negative. The absorbed element is getting consumed, so we write as negative. K2 into, what does this become? M absorbed plus the fraction absorbed is theta, so K2 theta. So here we are saying it's a following Langmuir isotherm, which says that all the sides are energetic equally, and the species in the surface that are exposed to the solution, they are the ones who are participating into the reaction. That is like what is beneath doesn't get involved. And then we say that the intermediates are not have, which are absorbed on the surface in the adjacent side, they do not have any interaction, and all the sides are equal, and the probability of getting the electron to lose from any of the atom, they remain equal. So this is what the isotherm, Langmuir isotherm, based on which we are doing the derivation. Now the next one is the Temkin isotherm, which we can also, which is complex. If we are considering that the equation we are using gets complex, we'll be seeing in the coming classes. So according to this, the sites have different energy. They have irregularity. The species gets absorbed early on easily absorbed surface, and they get absorbed last on a irregular surface. So there is like some sites have more affinity on which the intermediates can get absorbed. All depends upon the surface of the intermediate. Surface of the and that on the metal surface. The Frumpkin isotherm, that is different in terms of adsorbed species that have the tendency to adsorb closer to the previously adsorbed species. So you should understand here. Previously, according to Langmuir, all the sites are equal. There is no interaction, etc. Here, Temkin says no, all the sites are not equal. They have irregularity. Some of them get easily adsorbed on some sites, while the some sites they are regular. There are difficulty in getting absorbed, and they get absorbed at the end. Now, Fromkin says these species gets absorbed on the surface based on its affinity to get absorbed closer to the one where a previously species has been absorbed. This means there has an interaction between the absorbed species. So, this is what Fromkin says. So now let's write the mass balance equation. This we already wrote. Gamma d theta by dt equal to k1 1 minus theta minus k2 theta. Now at steady state, we are saying that the d theta by dt is zero. So we can equate them to zero. We are opening the brackets. In there only one adsorption it becomes easy. What is the fractional adsorption of theta at steady state? Steady state. So this is at steady state. So what does this mean at steady state? So when K1 is very small, what happens? Theta tends to 0. That means there is no surface which is absorbed by any intermediate. And when K1 becomes very large, K2 can be neglected, theta becomes 1. That means the entire surface is absorbed by an absorbed intermediate. And in that case, we get an equation like this. Now we are going to write out the chart. First, we wrote the mass balance. Now, what we're going to write after charge balance, we are going to see what is the current. So, we know only the first step has this NF into rate of the reaction. This NF into rate of the reaction. So, rate of the reaction is all the steps where the electron transfer is getting involved. In this case, only in the first step, we have electron transfer. So, only in that step, the electron transfer is happening. So, that is what corresponds to current. Other stuff doesn't give rise to any current. So, we write it as F into K1 1 minus theta. K1 is K1 DC into 1 plus B1 EAC. Now we know that. Then theta also has an expression. We derive it. We say theta SS plus theta dash EAC. So this two you need to know by head. K1 equal to K1 DC, E1 plus B1 EAC, and how theta is varying with the EAC. So substitute both of them into the IF equation. We get something of this form. Rearrange. We will get two parts. One due to IF DC and other due to IF AC. Get all the terms correspond to IF AC. Now rearrange it so that, yeah, Before that, this equation has a theta dash. Now, how to find out theta dash? We know we did that, and we get how to find out theta dash. We have the mass balance equation, and mass balance equation has d theta by dt. This derivation shows how we can derive for d theta by dt, and we get j omega theta dash EAC. Substitute this in the mass balance equation. Okay, and then you will get, when you solve it, you will get something in terms of theta dash. Substitute it back into IF equation, and whatever you get, then we are then EAC by IF is nothing but ZF. Then rearrange it, you will get the ZF. Finally, you have to also consider this due to the double layer capacitance, and you will have a total equation. Yes, so this is what we saw in the last class. So what all we need to keep in mind when you're given an step reaction mechanism, it will have both the electrochemical step and chemical step. Sometimes chemical step may not be there, only electrochemical step will be there. So we have to check that. Now, mass balance equation, we consider all the steps where one particular species adsorption is probably mx of plus, or I can say it is occupying theta space. So steps which involve the formation of theta and consumes theta, all those steps need to be consumed. That is, both these EC, that is electrochemical and chemical step needs to be considered. Then what you do steady state mass balance, you find theta SS. Then you have to find out IF. For finding IF, you have to only consider the electrochemical step. Then when you get it, separate out IF AC and IF BC. So this IF AC will have theta dash. Then you have to find out theta dash. So that we have to give d theta by dt equal to j omega gamma theta dash EAC. J omega theta dash EAC. Gamma is already coming from mass balance equation. Substitute this in back into the IFAC equation, you'll get ZF. Now, after finding out ZF, you have to do 1 by ZF plus J omega CDL to account for the total impedance also rising from the double layer capacitance. So, this is how you have to approach the question. Then we saw different problems. How to find out cathodic current, where the backward reaction, anodic current, forward reaction, etc. Then, yeah, this is where we stop. Now we are going to class 7. So let's see what we are going to look into in this EEAR negative resistance. Then we look into three-step reaction with adsorbed intermediate. Yeah. So this is going to be a little lengthy, the entire class. So what I'll do is I'll do EEAR mechanism, and then I'll see the assignment question from that part. Once that is completed, we'll go to three-step reaction and its question. Probably if you won't complete today fully, we'll look the rest of the part for the next class. Okay. So we'll first go for EEAR mechanism. Okay. So what is EEAR? So E here corresponds to electron transfer reaction. Then EAR corresponds to electron adsorption reaction. So it has an electron transfer as well as an adsorption reaction which is happening. So the two steps which are happening. So here what happens is there is an electron adsorption reaction which involves electron transfer. And so I'm writing that can be written as P solution K1 Q solution plus electron transfer. So this is the electron adsorption reaction which is involving electron transfer. Now, besides this, there is also contaminant that is present, which is reversible reaction. And that is given as A, that's there in the solution, which is getting, it's a reversible reaction. So it is getting adsorbed or it is getting adsorbed over the surface. So it is a reversible reaction. So it involves both electron adsorption reaction as well as a contaminant which undergoes electron transfer reaction. So what is happening? When we are applying a large overpotential, positive potential, positive potential will actually help the forward reaction where the oxidation is happening when we are applying a large overpotential. So similarly, when I am applying a large overpotential for this reaction, what happens is it will result in the forward reaction and the surface coverage of the AHR will increase. And this AHR will be then blocking the surface. Okay, and only the free surface which is available for the catalyzing the reaction of P solution to Q solution. Is it clear? I'll write down. When large overpotential is applied, positive, that is important. Forward reaction increases and surface coverage of A adsorb plus increases. So what does that do? So most of the A adsorb blocks the surface. Only free surface can catalyze this reaction. So here the adsorbed intermediate plays a role by blocking the surface and thereby hindering the main reaction, electron adsorption reaction. So the first step, which is P to Q, you see this has no adsorbed intermediate involved, right? So the first reaction will happen only if the surface is not blocked by the contaminant. So the first reaction is similar to the reaction mechanism that we saw first. Which one? The ferri and ferrocyanide. Fe2 plus giving Fe3 plus plus. So here in order to have this reaction happening, no intermediate is available, right? So the same as that. So here P to Q, this is the main reaction we are considering. And here there is no adsorbed intermediate involved. But what is happening? The available, but how is it different? But available surface is different. And this is dependent on contaminant. So this is how it is different from the first reaction we are saying. Here the important reaction or the main reaction is P giving Q, but the problem here is that it doesn't have any reaction at some point. Everything is correct, but here the problem is the surface will be available for the reaction is dependent upon the contaminant we are having. Okay. So yeah, so let's see into the yeah. Just give me a moment. So now let's see how we can write the reaction mechanism. So first step, let's write down the rate expressions. So let me write down the mechanism once again. P solution giving Q solution plus electron and K1. And the next step, A solution minus K2, K minus 2, A XOR plus electron. Yeah. Now let's write the rate of reaction of the first step. So what is it? So we know here the theta. So we have contaminant in the solution, and when we are applying a positive overpotential, some amount of that gets absorbed on the surface of the metal or our free surface. So here theta corresponds to the fraction of surface occupied by A, A absorbed. Also, that is not the main reaction. So what is the fraction of side absorbed by P solution? So P solution can get converted or into the Q solution only if that surface is free and is not absorbed by A absorbed. That means that becomes 1 minus theta. So is that clear? Is that concept clear? So what is rate of the reaction? K1 into P solution. This is a rate and this happens at 1 minus theta. Now what is R2? R2 equal to K2 into. So because it is in solution, we have to consider the concentration. A solution minus into theta. Now R minus 2 is what? K minus 2. A absorbs concentration is theta. So these are the rate steps. Now, so this is the first step. We have written the mass balance. Sorry, rate of the expression. Now what is a mass balance? For the mass balance, we have to consider all the reactions in which there is a formation or consumption of A solution minus, or sorry, A adsorb, the formation and consumption of theta. So that means we won't be considering which step. Okay, let me write down. Gamma d theta by dt equal to P solution gives K1 Q solution plus electron. Is there any formation or consumption of theta in that? No. So we won't be considering that step. Then which step will be considering? We'll be considering K2 into here it is formation of theta. So I'll just write that before. So first the reaction we won't consider because there is no formation of consumption of theta. R2, yes, there is a formation of theta. And R minus 2, yes, there is a consumption of theta we'll consider. So the expression becomes R2 where there is formation of theta minus R minus 2. Now what is R2? R2 is K2 A solution minus theta minus K minus 2 theta. So this is the expression for the mass balance. Now after this what we do? What is the next step we do? After writing the rate and the mass balance. The next one is steady state mass balance so that we can find out theta SS, right? So I'm equating d theta by dt to 0. And what does this become? K2 A solution minus theta minus K minus 2 theta. I'm really sorry. I have made a mistake here. I'm sorry, I've made a mistake here. I didn't notice it. I just noticed it now. And that being, see, theta is the fraction of surface which is occupied only by A adsorption. So what is the fraction of side which is absorbed by P solution? 1 minus theta. Now, what is the fraction of side absorbed by A solution minus? That is also 1 minus theta. So 1. So whatever is not occupied in that space, in that space, either P solution or the A solution minus can, A solution minus can continue to form AHR species, or P solution can compete to give Q solution. So I made a mistake, and the mistake is here. I'm rubbing it. It is, what is the fraction of side available? It is 1 minus theta. Similarly, I made a mistake here. I just write it as K2 A solution minus 1 minus theta minus K minus 2 theta. So this is the total expression. So same mistake I made over here. I'll just rub it and write 1 minus theta K minus 2 theta equal to 0. Now what is happening in steady state? Let's rearrange. A solution minus equal to K2 A solution minus plus K minus 2. What is it? At steady state becomes theta SS, and theta SS becomes K2 A solution minus by K minus 2. So it's steady state. I can write it as DC. Everything becomes DC because it's a steady state. So get this in mind because I've made a mistake, and that is fraction of sides is occupied by A absorbed is theta. The rest of the side is 1 minus theta, in which either P solution can in that side either P solution can get converted to Q solution, or A solution minus they can again get converted to A absorbed. So that is what 1 minus theta sides are about. So R2 becomes K2 A solution minus 1 minus theta, and R minus 2 is K minus 2 theta. So yes, we have found out the steady state step. So now the next step involved is to find out what is the current density IF. So this is the next step. And how do we do that? So here we have to consider all the reaction that involve electron transfer. So IF becomes, if you remember, the first step, it involves electron transfer. Second step and the backward step also involves electron transfer. So all the step is considered for finding out the current density. And here, all the forward reaction is positive rate and the backward will have negative rate. So it becomes NF R1 plus R2 minus R minus 2. So this is what you get. Now let's substitute and find out. IF equal to F. All are having single electron transition, so we write N equal to what? So it is K1 P solution 1 minus theta plus K2 A solution minus 1 minus theta minus K minus 2 theta. So this is the expression. So here, what we are considering is this particular expression when we are trying to say solve, we are going to do it in kinetically limited region. What does kinetically limited region means? That is, the reaction rate is dependent only upon, sorry, the current depends on the rate of the reaction, and there is mass, I mean, the material is abundantly available. Only if you go to the mass transfer limited region, the reaction becomes limited by the availability of the material. So if that becomes the case, then the concentration, B solution, A solution, all will keep on changing. The reaction solving the reaction becomes more complex. Here, when we are saying kinetically limited region, we have abundance of reactants. Only thing is, here it is dependent only upon the rate of the reaction, not by the availability of the reactants and products. So when we say it's kinetically limited, this means P solution and P solution minus they are available in abundance and they can be considered constant. That means it is not hindered or there isn't any hindrance to supply of these materials. So they are considered constant. Now we know what we have to do. Theta is theta SS plus theta dash EAC. Same way K1 becomes K1 DC into 1 plus V1 EAC. Similarly, K2 equal to K2 DC 1 plus V2 EAC. K minus 2 equal to K minus 2 DC 1 plus B minus 2 EAC. So these are the rate constants and the theta value we need to consider when solving. Now substitute all into IF equation. What do you get? F equal to K1 becomes K1 DC 1 plus V1 EAC. P solution 1 minus theta SS minus theta dash EAC. Now the next chain is K2 DC 1 plus V2 EAC. A solution minus 1 minus theta 2 minus theta 2 dash EAC. Last term is K minus 2 DC 1 plus B minus 2 EAC and plus it is theta, so theta SS, so it's not theta 2 or theta, only one theta is there. Plus theta dash EAC. Now, what we have to do? We have to simplify. This is gonna be a little complex. Please, like rather than just copying it from me the way I have done, try to solve it yourself and then cross check. Else you may end up making mistakes. So let me start. So F into K1 DC P solution 1 minus theta SS minus K1 DC P solution theta dash EAC. Now I'm gonna do with V1 EAC. V1 EAC becomes K1 DC V1 EAC P solution 1 minus theta SS. What about the next term? K1 DC V1 EAC P solution into theta dash EAC. There is theta dash into theta dash, sorry, EAC into AC, that means AC square, value small, so we can neglect it, we don't need to consider that. So we are avoiding it. Now, the next term, that is K2 DC A solution minus 1 minus theta SS minus K2 DC B2 EAC K2 DC into A solution minus theta 2. So there is no theta 2, only one theta. I wrote it by mistake. Theta dash EAC plus K2 DC B2 EAC A solution minus 1 minus theta SS. So I'm avoiding again the next term, that is K2 DC B2 EAC A solution minus theta dash EAC, because there are two EAC square. So into AC, that means AC square. So I can avoid that. Now let's come to the next one, minus K minus 2 DC theta SS minus K minus 2 DC theta dash EAC minus K minus 2 DC B minus 2 EAC theta SS. The last term, that is K minus 2 DC B minus 2 EAC theta dash EAC is ignored because EAC square can be neglected. Now what is the next step? We have to omit all the terms where there are only constants. That is, there is no theta dash involved. Why? Or there is no EAC. Why? Because all the steps corresponds to the Faraday current due to DC current. So that means the first term is neglected, this term is neglected, this term has, this term has, this term has, this term has, this term can also be neglected. All the other terms we can consider. Now, what we can do is, we can rewrite it such that we are considering all those terms that has theta dash, and we have all those terms with EAC. So if I write that, this becomes IF. EAC will be in common. You can see this term has EAC, this term has EAC. All those terms, they correspond to Faraday current. I'm taking out EAC. Now the first step, let's consider all the steps where there is no theta dash involved. That becomes K1 DC, B1, P solution, 1 minus theta SS. Let me write it next page. I don't want to make it consistent. IF AC equal. Let me take out EAC, as I told all the terms are. Now I'm going to write the terms without theta dash. So the third term, this term, doesn't have theta dash. K1 DC B1, P solution 1 minus theta SS. Okay, I've finished considering that term. The next term has theta dash, but the next term K2 DC B2 A solution minus 1 minus theta is doesn't have. Now let me see the last term, that also doesn't have theta, theta dash. So that becomes minus K minus 2 DC B minus 2 theta XS. So all these terms are those without theta dash. Now let me write down all the terms with theta dash. That is the second term, minus K1 DC P solution theta dash. Now 1, 2, 3, 4, fifth term has theta dash minus K2 DC solution minus theta dash. Second last term also has that Now what we can do is we can rearrange it so as to rearrange it so as to get Impedance. How does it come? VAC, V1 VAC, V1 is solution. One minus EIS plus theta DC V2 is solution minus 1 minus theta SS minus K minus 2 DC V minus 2 theta SS minus theta dash K1 DC P solution plus K2 DC A solution minus plus K minus 2 DC. So this is the full equation. Now what we have to do? We have to find theta dash. How to find out theta dash? So we have found out, we started with the rate, mass balance, steady state, current density. We solved and we have found out IF. This IF AC. Because we have to cut out all the terms where constants are there that corresponds to IF AC. Yeah, here we have written IF AC. So we add on. And we have found out IF AC. Now next step, find out theta dash. So how to do? You have to go for mass balance equation. That is gamma d theta by dt is equal to R2 minus R minus 2. K2 A solution minus 1 minus theta minus K minus 2 theta. So now how to find out? We have to substitute for theta. That is gamma j omega theta dash EAC. Now substitute for everything else. K2 DC 1 plus B1 EAC A solution minus 1 minus theta SS minus theta dash EAC. Minus K minus 2 DC 1 plus B minus 2 EAC theta SS plus theta dash EAC. Now if I solve it, I'll get K2 A solution minus 1 minus theta SS minus K2 DC A solution minus theta dash EAC plus K2 DC V1 EAC A solution minus 1 minus theta SS. So from the last term, that EAC square, it will go, it won't be there, so I'm not writing. Then minus 2 DC theta SS minus K minus 2 DC theta dash EAC minus K minus 2 DC B minus 2 EAC theta SS. So again the last term goes because it has EAC square. Now let me cut down all the terms where EAC is not there. This term doesn't have EAC. This term doesn't have EAC. Now let me cut down EAC from all the terms. This one has EAC. This one EAC. This one EAC. This one EAC. This one EAC. Now let me rewrite such that theta dash terms comes one side. That is j omega gamma plus K2 DC a solution minus, that is this term. Now this one doesn't have theta dash, this one has K minus 2 DC. Now this equal to, that is this term. There is one term here and one term here. So this term comes from B1 K2 DC B, so I'm going to say B2 EAC. So K2 DC K2 DC B2. So let me write that down. I'll write it in the next page. That's better. Theta dash J omega gamma K2 DC A solution minus plus K minus 2 DC we get, and that is equal to K2 DC B2 A solution minus 1 minus theta SS minus K minus 2 DC B minus 2 theta SS. So this is what we got. Now we know the rate for the first step. I mean second step. What is it? K RAF 2 equal to K2 A solution minus 1 minus theta. Rate of forward reaction should be equal to rate of backward reaction. Right? So if I see rate of forward reaction becomes K2 DC 1 minus at steady state. So it is 1 minus theta SS A solution minus, and that should be equal to K minus 2 DC theta SS, right? Forward reaction should be equal to backward reaction. So if I substitute that, your expression for this one, if I'm substituting for this one, this part, if I'm substituting by K minus 2 DC theta SS, this becomes K2 DC. So I'm substituting for that. So this entire thing, K2 DC 1 minus theta SS and A solution minus, I can substitute it by K minus 2 DC theta SS. I can take that as a common. So that is what it means. And I'll get B2 minus B minus 2. So if I'm doing that, this becomes J omega gamma K2 DC A solution minus plus K minus 2 DC equal to, I'm just taking that out, K minus 2 DC theta SS B2 minus B minus 2. So finally, theta dash equal to B2 minus B minus 2 K minus 2 DC theta SS by J omega gamma plus K2 DC A solution minus plus K minus 2 DC. So this is the expression you are getting for theta dash. Now substitute it back into this expression for IFAC. What will we get? Let's write IFAC equal to B1 K1 DC P solution 1 minus theta SS plus B2 K2 DC A solution minus 1 minus theta SS plus K minus 2 DC B minus 2 DC theta SS. Okay, let me write that one first. If AC equal to F to B1 K1 DC P solution 1 minus theta SS plus B2 K2 DC A solution minus 1 minus theta SS minus B minus 2 K minus 2 DC theta SS minus K1 DC P solution K2 DC A solution plus K minus 2 DC K1 DC P solution plus K2 DC A solution minus plus K minus 2 DC into theta dash, where the theta dash value is given as B2 minus B minus 2, the whole bracket into K minus 2 DC theta SS, the whole divided by J omega gamma plus K2 DC into A solution minus plus K minus 2 DC. So yes, this is how what to say, this reaction is derived. Now let's just look into the interpretation. So what is happening here? I hope this expression is clear. There is a full thing that you have to do. So I hope this is clear. Now let's see how does this vary. So what is happening is when the current, so here when we are increasing the what to say, lower potential in positive direction, what happens? Initially, both the reactions are happening. Reaction 1 and reaction 2, right? Reaction 2 is because of the contaminant, and the reaction 1 is because of P solution giving Q solution. And this contaminant was A solution giving A adsorbed minus plus electron. But after some time, so initially with the EDC increases, current also increases. But after some time, this increases so much that what happens? The most of the site is covered by A adsorb, and very less sites are available for the reaction that we wanted, the P solution and Q solution to get catalyzed. Very less amount of space available. So this means initially the ferrite I versus EDC. Initially, with the increase in EDC, it keeps on increasing, but after a point, it decreases because the surface is covered by the contaminant. So, if you are taking an what to say, at any EDC up to this point, it has positive current. So when it is we are taking differential impedance and not the at that point. So what does it mean? So when EDC is low, when at that point this current keeps on increasing, you get an what to say impedance where it is actually in the positive side. Real axis, the real part of the imaginary, the real part is always in the it's in the positive side, positive x-axis. Whereas when we are going to this area, just give me a moment. Hello, hello, hello. So yes. Hmm. So when we are going for the case where the DC potential is such that the current reduces with the DC potential, if any of these points, if we do the impedance, we'll get a negative impedance. Why? Because the differential impedance is considered and that is negative. We'll get something like this. This is for this system for a given particular value, but the idea over here, graph can be anyway, but when you are doing it for the points where the current is reducing with the potential, you will get a negative impedance, right? This was IFAC by EAC, so that is YF. I made a mistake. Yeah. So by this, we have finished looking into EEAR, where we have the surface catalyst. We have one particular reaction that we want to happen, and that is we giving you solution. But here there is a competing reaction which is happening, where from the solution there is some contaminant that can get absorbed on the surface of the catalyst under the reaction is happening. So adsorbed intermediate is coming from the contaminant reaction, and the actual reaction is a single step reaction without any adsorbed intermediate, similar to the first reaction mechanism we have seen. This is the third reaction mechanism we have seen. The first reaction mechanism, ferrocyanide, ferricyanide, that one. Second, we saw with one adsorbed intermediate. This is also third one is a one adsorbed intermediate, but it is kind of a case where it's same as first one, but that the entire surface is not available for the reaction. Part of the surface is occupied by the contaminant. Yes, with that, we have finished doing this problem. Now, let's move on to the problem part, assignment number 6. Then we'll go for seeing the case where we have two adsorbed intermediate. How to do that, we'll see then. Okay. So I'll first write down the question. Writing down the question. So here the questions up to question number 6 is from the EEAR mechanism. Consider the reaction P solution gives Q solution plus electron. This is the same as what we saw now, but we have numerical problem from that. Yeah, I'm writing down the question. And the question says the kinetic parameters are given by K10 equal to 10 to the power minus 5 centimeter per second. V1 equal to 20 volt inverse. K20 equal to 10 to the power minus 6 centimeter per second. V2 equal to 20 volt inverse. K minus 20 equal to 10 to the power minus 6 mole per centimeter square per second. And V minus 2 equal to minus 18 volt inverse. Gamma equal to 10 to the power minus 8 mole per centimeter square. They have also given that I'm writing all the parameters in one page, then it becomes easy to see. So P solution equal to Q solution equal to A solution minus equal to 100 millimolar. Remember, 1 molar equal to 1 mole per milliliter is equal to 10 to the power minus 3 moles per centimeter square. 1 mole equal to 10 to the power minus 3 mole per centimeter square. Now, the question is at EDC equal to 0.25 volt versus OCP, what is the fractional surface theta SS? Okay, so we already know how to do this. It's kind of a relation on derivation. I'm not going to spend time on derivation. So how to do it? The theta SS, it comes from which equation? A solution minus gives K2, K minus 2. It becomes A adsorb plus 1 electron, right? So K2, A solution minus 1 minus theta equal to K minus 2 theta. So at steady state they are told. So that becomes equal to 0. And finally theta SS is equal to K2 DC A solution minus by K2 DC A solution minus plus K2 K minus 2 DC. Right? How do we get this? We have seen in depth over here. So here only the second step and the backward of the second step corresponds to the formation and consumption of theta, because the first step does not involve the formation of adsorbed intermediate. So we have considered the same steps and we are then equating it to 0. So this is what I'm talking about. And then we equate it to 0, we finally get this as the expression. So let's solve it. So what is K2 DC and K minus 2 DC? What is A solution minus? A solution minus is given as 100 millimolar. So that becomes how much? 0.1 molar. And that is 0.1 into 10 to the power minus 3 mole per centimeter cube. So we got A solution minus. Now what is K2 DC and K minus 2 DC? What are the values given to us? K10, K20, K minus 20. We know K2 DC becomes K20. It's exponentially related to the potential, DC potential. What is K2 DC? It is 10 to the power minus 6 exponential V2 is 20 into 0.25, and that value is, let me calculate. This becomes 1.48 into 10 to the power minus 4. Unit same as that of this, so K20 centimeter per second. Now same way K minus 2 DC we'll find out. And that is K minus 20 exponential of B minus 2 EDC. K minus 20 is 10 to the power minus 6 exponential B to the power minus 2. B minus 2 is 18.25. Minus 18, don't make a mistake. Let me just see if I really. Yeah, it's minus 18 that I've written here. Exponential of minus 18 into 0.25. This gives you 1.11 into 10 to the power minus 8 moles per centimeter square second. Now, what is theta SS? We can substitute all the values. K2 DC 1.48 into 10 to the power minus 4 to A solution minus 10 to the power minus 3. Same thing again, 1.48 to 10 to the power minus 4 into zero point 0.1 into 10 to the power minus 3 plus K minus 2 DC 1.11 into 10 to the power minus 8. 10 to the power minus 4 into zero point 0.1 into 10 to the power minus 3 is nothing but 10 to the power minus 8. It's in common in all the terms, so I'm going to cut it. Now what does it become? 1.48 by 1.48 plus 1.11, 1.48, 1.59. I think I made a mistake somewhere. So it's 2.59. Sorry. And you will get the answer as 0.572. I think that is within the range which is told in the question. And that means the range is given as 0.56 to 0.589. I'm getting 0.572. Yes, so this is the correct way and I've got the right answer. Okay. Now let's go to the next question. At the same potential, which is EDC equal to 0.25 volt versus OCP, total Faraday current is given by equal to dash milliamp per second as well. So they have asked for Faraday current because of DC current only, not AC. So how do we do it? So we have already seen. I'm not deriving it again. Same thing. So this is the total Faraday reaction. So for DC current, what happens? K1 becomes K1 DC, K2 is K2 DC, K minus 2 is K minus 2 DC. Theta becomes theta SS. That is the only thing. Keep that in mind. You don't have to derive it or anything. IF DC means in IF equation, K is K DC and theta becomes theta SS. That's all. So IF DC equal to F into K1 DC P solution 1 minus theta SS plus K2 DC 1 minus theta SS. I'll just write in the next. K2 DC 1 minus theta SS. A solution minus K minus 2 theta SS. Yeah. So this is the expression. So K2 we already found it as 1.48 into 10 to the power minus 4. K minus 2 as 1.11 into 10 to the power minus 8. Now, keep in mind both the questions are linked. So, if you are making mistake in any of the numerical problem, then your subsequent questions will also get wrong. So, if you wouldn't have got, if you had got your first question correct, then your second question would have also gone wrong. Okay, so you have to be careful when you're doing numericals. K2, K minus 2 is already known. We did it for the previous question. P solution equal to A solution minus equal to zero point 0.1 into 10 to the power minus 3 mole per centimeters cube. This also we know. Now how to find out K1 DC? K1 DC equal to K1 naught exponential of B1 e to the power EDC. Sorry, EDC. K1 0 we have written as 10 to the power minus 5. Exponential of B1 EDC. B1 is 20. EDC is 0.25. So it is nothing but 5 equal to 148.41 into 10 to the power minus 5 moles per centimeter of something, whichever the unit of that setting. Okay, once you get this, you have got all the values. You have to substitute it and find the solution. Let me substitute it. F 96,485. K1 DC is 148.41. 10 to the power minus 5. 1 minus, okay, P solution is 0.1 into 10 to the power minus 3. Theta 1 SS, theta SS is 0.572. Plus K2 DC 1.48 into 10 to the power minus 5. 1 minus theta SS into A solution minus. A solution minus is 0.1 into 10 to the power minus 3 into 1 minus 0.572 minus K minus 2 DC is 1.11 10 to the power minus 8 theta SS 0.572. What can I do? First thing I'm going to take 10 to the power minus 8 outside because 5, 10 to the power minus 5 into 0.1 and 10 to the power minus 3 is minus 0.8. So, this This is here. This, yeah, I'm gonna take that out. This is for making it easy or look simple. Else it looks so huge. So then the next term is 148.41 into 1 minus 0.572. What is 1 minus 0.572? 1 minus 0.572 equal to 0.428. Next term is 1.48 into 0.428 because again it's 1 minus. Next term is 1.11 into 0.578. Whatever answer you get over here, it's gonna be in what unit you have to see. Uh, this is all mole per centimeter square, mole per centimeter square, it's okay. So here, this is coulombs per mole. These all are gonna be mole per centimeter square per second. Okay. So coulombs means ampere second. So by mole. And here also mole per centimeter square second. Centimeter will stay there, mole and second will cancel. It's going to be an ampere per centimeter square. Just keep in mind. How much is the value? So you're going to get 148.41 into 0.428, 63.52 plus 1.48 into 0.428, 0.64 minus 1.11 into 0.578. 0.64 actually. So I'm going to just cancel this out. And there's a 10 to the power minus 8 over here. I was just wondering where it went. Okay. So now 96,485 into 63.52. Okay. Divided by into 10 to the power minus 8. So you'll get point. We'll get point 0. Yeah, you're gonna get something like this. I've got this as ampere per centimeter square. If I have to make it into milliamps, I'm going to just multiply it with 1000, 6.1 milliamp per centimeter square. Just give me a moment. Yeah, so I made again a mistake. So this is 10 to the power minus 5, 10 to the power minus 3, and a point 1. So it is 10 to the power minus 9, not 10 to the power minus 8. So what I'm taking out is not actually 10. So this value 10 to the power minus 9. So accordingly, there will be small changes because 0.064. I cannot cut this out. 0.64 minus 0.064 roughly. When you do this, you will get like this 6.12 milliamp per centimeter square. Okay. So yeah, this is what I finally got the answer as. Now the next question. Your next question is, at the same DC potential, ES data is acquired using small amplitude perturbation, charge transfer resistance. Okay, so first thing that you have to understand is what is charge transfer resistance and what is the next question talks about what is polarization resistance. So charge transfer resistance is when omega tends to infinity, right? So let's do it. So how do you know? First we have to take YF value. What is YF value? This you have to do it on your own. It will take more time. Okay. But first let me write out YF. The experiment, the impedance or the admittance we have written. F into B1 K1 DC. That equation, that full equation you have to write out. P solution 1 minus theta SS plus B2 K2 DC A solution minus 1 minus theta SS minus B minus 2 K minus 2 DC theta SS. Then you have minus K DC B solution theta DC A solution minus plus K minus 2 DC theta dash. Theta dash. Theta dash. Now what is theta dash? I'm going to write it separately. B1, B2, B minus 2, K minus 2 DC theta as a j omega gamma K minus 2 DC plus K2 DC A solution minus. Yeah. B2 minus B minus 2 K minus 2 DC theta SS by K2 DC A solution minus plus K minus 2 DC plus j omega gamma. So this is over here. So now the problem here given is RCT. So when you find RCT, this is a case when you have the impedance. Okay, impedance when omega tends to infinity. What is the value of the impedance when omega tends to infinity? That gives you the charge transfer resistance. Now, for that, where does that omega comes here in this equation? Here we have YF. So YF is nothing but plus 1 by ZF. So once I find out YF, I can just take the inverse, I'll get the impedance value. Now, when does omega tends to infinity over here? Where does omega comes? It is not there in any of the terms, but in the theta dash. This term has theta dash. I mean, this term of theta dash has omega. And it's in the denominator. So when omega tends to infinity, what happens to theta dash? It tends to 0. This entire term tends to 0. And this is multiplied by another term. K1 DC P solution plus K2 DC A solution plus K minus 2 DC into theta dash. The entire term becomes 0. If in that case, how will I simplify this? Becomes F into P1 K1 DC P solution 1 minus theta SS plus B2 K minus K2 DC A solution minus 1 minus theta SS minus B minus 2 K minus 2 DC theta SS. Did I find something of this form? Now, have to solve this. This is how I've simplified YF. So why did I do that? RCT is nothing but the impedance when omega tends to infinity. And when omega tends to infinity, the theta dash versus 1 by j omega that tends to, because this is infinity, the entire term tends to 0. 1 by infinity is 0. And multiplied by that 0, this entire term goes off. And this is a simplified version of YF. Now let's do this. B1 K1 DC F is 96,485. B1 K1 DC. B1 is not there, but K1 DC P solution 1 minus theta SS. I already found out. Okay, anyway, I'll do that. So B1 is 20. K1 DC P solution into 1 minus theta SS is nothing but this value. So that is 148.41 into 0.428 into 10 to the power minus 9 plus B2 is again 20 into K2 DC into A solution minus into 1 minus theta, that is 1.48 into 0.428 into 10 to the power minus 9, and B minus 2 is 18, K minus 2 DC theta SS, that is 1.11 into 10 to the power minus 8. I'm writing 0.11 to 10 to the power minus 9 into 0.572. So this is like an easy way of just copying from that. Except that same, except that it doesn't have the B1 value, otherwise it's the same. Now I'm taking 10 to the power minus 9 outside. Now simplify it. Let's do it. 20 into 148.41 into 0.428. It's nothing but 1270.4 plus next term is 20 into 1.48 into 0.428. 12.7 plus, so it's negative 18 into 0.111 into 0.572. 1.2. Now find out the entire value 96. So let's do it 1270.4 plus 12.7 minus 1.2. Okay, you get an answer multiplied by 96,485 into 10 to the power minus 9. So this entire thing when I did, I'm getting 0.12. Okay. Now if I'm taking the reciprocal, so that is YF value. Okay. It is YF value. Now what I need is reciprocal of that to find out the impedance. So 1 divided by 0.12. It's actually 1 3. I'm getting 0.1236. Let me, I have got it as point, yeah, 0.136 actually. So I'm taking it as 0.14. Okay. I'm rounding it out to double digit. And when I'm taking the rest. So what I got is YF as 0.14. Now what did I say? The RCT is the value of impedance when omega tends to 0. So ZF equal to 1 by YF equal to 1 by 0.14. I'm getting 7.14. It's correct on the border. So it depends on where you are. So here and all, when I'm actually doing it, I was taking only the first decimal by rounding it up. So I was actually taking the higher value. So probably that would have led the value to reach close to that higher value bit. So be careful when you're doing it. Yeah. So this is how you get the value. So whatever the unit, ohm, centimeter square, whatever that comes. Now, now the next question is, at same DC potential, EIS data is acquired using small perturbations. What is the polarization resistance? So same thing. The theta dash equation has a something plus j omega gamma, right? So when is RP? RP value we get when ZF with omega tends to 0 or 1 by YF where omega tends to 0. So when omega tends to 0 in this theta dash, this value becomes equal to 0. But you have the rest of it. So how do you proceed with this question? I wouldn't be doing this. It is same. Except that you will have an additional term. Which additional term? Here we said this term, theta dash term tends to 0. But here this theta dash exists except that j omega gamma is 0. So this term theta dash value comes. So in that YF equation, K1 DC P solution plus K2 DC A solution plus K minus 2 DC term comes along with that into theta dash. So when we did for finding RCT, we have not considered from this part. But when we are doing for R P value from this part till this much you need to consider. Okay, so first find out theta dash. We'll have omega tends to 0. Find out theta dash, substitute in YF. It is pure mathematical. It is little more lengthy. Find out YF. Then from that, YF equal, ZF equal to 1 by YF. This value which you get is RP because we are considered omega tends to 0. That is the upper. So is that clear? So this is how you have to what to say approach with this question. Okay. So with that, I'm skipping this question. You have to do, and the value should come between minus 100 and minus 90 ohm centimeter square. So the same as before. That's why I'm not doing. Except its calculation is little lengthy. You have to be careful when you're doing. When I make mistake, you have to be careful. Only then you can get it correct. Now let's go on to the next question. They have given you the polarization figure, and it is something like this. This is approximately 1, this is approximately 0.5, this is 0, and this is 1.5. This I in milliamp per centimeter square. So now they're saying there is an impedance spectra. This is a polarization data given, and they're saying impedance spectra acquired at EDC equal to zero point 0.7 volt versus OCP. Then what is RP expected to be? Positive. So the options are negative, positive, either positive or negative or zero. Now let's see. As we told, this is the case with EEAR where there is when we are applying DC potential for the positive potential, after some time the production of the desired FFP giving few solutions happens, and then the current keeps on increasing. But when the value increases after a point, what happens is it is actually counteracted by the forming extra additional formation of what to say a solution minus, which actually hinders the reaction. The contaminant gets absorbed and thereby they hinder the reaction. So that's why after some time the current actually reduces. So zero point 0.7 volt there, in that case the impedance becomes negative because we are considering the differential impedance. 0.7 comes somewhere over here. So here the current is reducing with what to say the potential. So the option here is negative. So now that's how we have answered the which question is fifth. Now the sixth question is same, but here the value of EDC is given as 1.2 volt versus OCP. Let's see 1.2. It comes after 1, so it's somewhere here. So 1.2, and here here it is somewhere here, and it keeps on increasing with the potential. So here it becomes positive. The impedance is positive. Okay, so this is how we have to do. So in this class, we have seen how we are doing electrochemical reaction and the adsorption reaction together. So the differences anti-surface is not available for the reaction. It's partially covered by the contaminant. And in that case, how will the mechanism be? And we also solved that how to find RP, how to find out the current, how to find out the steady state theta value, etc. So I hope today's class was helpful for you. So with this, I'm going to stop today's class, and the next class we will see the three-step mechanism where we have two adsorbed intermediates. So here till now we are writing gamma d theta by dt equal to so and so reaction. That is because we have only one adsorbed intermediate. Now what will happen if we have two adsorbed intermediates theta 1 and theta 2? We'll write separately. That is the only difference, and the reaction derivation becomes little complex because when we have theta 1 and theta 2, we'll also have theta 1 dash and theta 2 dash. So reaction is little more complex. You have to find out more number of variables. Okay. So yeah, with that, I'm stopping today's class. Thank you all.